Okay, so welcome everyone. We're going to talk about digital processing specifically. I guess it comes under the umbrella of digital imaging in general, but specifically today we're talking about what happens after you've actually made the exposure and you either put it into a CR reader, your plates, or you just have a DR unit. So really what is happening in, I guess we could say, less than 30 seconds, right? CR takes a little bit longer than DR, so DR maybe 10 seconds. What's happening in between that raw image versus your final product, which you can decide, as many techs do, that they don't like it and they want to adjust things themselves. So we'll get to some of those things as well. So what do you see here? Let me dim the lights a little bit. This is called a histogram. We'll talk specifically about it in, I don't know, maybe 10 slides from now. But I want to start off by describing what's going on here so you have an idea. Essentially, picture, if you will, there's a communication between the data that you generate with your X-ray, right, which is based on, the anatomy and what exposure techniques that you set up, right? You create some kind of data, okay? Then, provided you choose the correct procedural algorithm, right, you choose the correct part, there is a set of data that is designed to represent the optimal contrast, optimal brightness for that particular procedure, right? Does that make sense? There is a communication that then has to take place between what you have generated and what the computer for that exam thinks is optimal. That communication takes place by one histogram essentially talking to a specialized histogram. So, what is a histogram? Very quickly, it is a graph that indicates all of the pixels that you have on your image and what brightness levels there are for those pixels. So each one of these bars, right, indicates a certain grayscale, right? So this might be oversimplified because, as we've learned with bit depth, you can have hundreds of grayscales, and it looks like we only have a few lines here. Okay, so this is not drawn really to scale, but if you imagine each one of these as a bucket, whatever this grayscale is in the middle over here is going to have, less of that particular gray, light gray, dark gray, whatever it might be, than these up here. And the idea is that the histogram that the computer has, which goes by a specialized name called a lookup table, is going to compare what it thinks is optimal compared to the histogram that was created by your exposure, by your raw data. So that's kind of the whole story. There are a few things that has to happen to make your histogram even viable to look at, right? So there are some things that happen. There are also issues that can occur, problems. So part of the lecture is what can possibly go wrong. So we start off with a misconception. There's some language that you may see, things like pre-processing versus post-processing. And really, I just want you to understand that there's really only one process. We call it pre-processing, but essentially, if you decide that you don't like the contrast or the brightness and you want to adjust it yourself with your mouse or, actually putting the numbers, or as I'll show you later, you can kind of pull on the histogram itself, you're really just asking it to redo this pre-processing again. It's not like it's going to do anything entirely different. It's just you saying, I don't really like it. So the actions between pre-processing and post-processing are pretty much the same. Things that you may like to do, a lot of techs do this. I don't know why. I understand images might not look as bright as they want them to be, or they don't like the contrast, but we shouldn't really manipulate those things because the monitors that we look at are not necessarily, and most likely not the same as the expensive monitors that the radiologists look like. And if we decide to change the image, change the brightness, change the contrast, crop the image, that's even worse, then you may be taking away or limiting the radiologist. They may not be able to uncrop. It might just be gone. They may be limited in their ability to window the contrast or change the level of brightness. Right. Now, in essence, pre-processing is where we look for errors and where the computer does a lot of analysis to look for things like, does it spot maybe a lead apron? Does it spot raw radiation that's outside of the field? Kind of looks at the image as a whole. And these processes happen in both CR and DR, but there are some distinct differences that we'll go over. So we're looking for pixels that might be turned off, right, known as dead pixels. So there are some fixing things that have to happen during the processing. So post-processing, again, is really just you manipulating the image that's already been manipulated to be optimal. Apparently, you don't like the optimization that the computer did. And lots of techs do this. And sometimes they're right. This is not a perfect science. They keep coming up with new and better algorithms. Images always just don't look perfect. But you have to be careful when you're doing that again, because you don't know what you might be changing that someone can not unchange. The reality, as it says at the bottom here, is if everything was perfect, there'd be no need for, in quotes, post-processing. So one of the first things that's important is what's known as flat field uniformity. The idea is you want the entire field, in this case, I'm not talking about the field of collimation. I'm talking about whatever is displayed on the monitor, to be of equal density, or brightness, I should say. So one way to test for this, and occasionally, right, this is done with an actual phantom, so unless you're doing QC or you're assigned to do this, it might be a physicist. They take an exposure with a phantom. The idea is the phantom is supposed to provide a uniform density. You can't do this on a patient because we have different things in us. So as a matter of fact, you're best not even using a phantom, right? Because that would just kind of throw errors in there. And the idea is to look at different regions. Displayed here, we have 5 little squares. And I don't know if you've seen this in clinic or here at the lab. Sometimes you can hover with your mouse. I know in our DR room, not the C-arm DR room, the fluoro DR room, you can do points and you can kind of click in any particular spot and get a brightness level. So the idea is your levels across the entire field should be within a certain range. They don't have to be the exact same number as illustrated here, but they should be within range. If they're not, then the sensitivity of your system might be off and needs to be calibrated. So this isn't something that the computer does on its own. This is a test that can be done. Now, assuming that your equipment is functioning, basically the rest of our discussion is what happens when images show up on your screen. So one thing that could be caused by a TFT, thin film transistor, we'll talk some of those specifics when we get to CR and DR. But there might be an issue where some of your pixels are dead. They're just black. This is an example of interpolation. Interpolation is a method or mathematical algorithm that takes known data, so you know the brightness levels of all the pixels except the few that are dead. Now let's say you know exactly the 8 pixel brightness levels that surround any one pixel. Logic says, especially since these pixel sizes are really small, right? They're sub-millimeter, that if the 8 pixels have a certain brightness level, the dead pixel's probably going to be somewhere in the ballpark of that brightness of the ones that are surrounding it. Let's turn it on and give it that brightness level. So the 8 surrounding pixels we call a kernel. The one is in the middle is the one that's dead. And interpolation is this mathematical method of taking the known data in multiple levels and trying to take unknown data, that being the dead pixel, and giving it a brightness level. So this theory of interpolation gets used not just for dead pixels, it's one example, but it's a way of saying, looking at my social network and saying, well, if people are a lot like me and this one person isn't, but they're friends with me, then chances are we have a lot of the same interests. In this case, it's our brightness level. And here are a bunch of other ones. So you have segmentation. That's the first one we'll talk about. And the second one we'll talk about is partitioned pattern recognition, or PPR. And you can see PPR is used only specifically in CR. Yes, it's a world of acronyms. The PPR goes to the CR, but it's not exactly the same as the EFR, right? Okay, so you can have fun with this. But all of this is going to lead to the construction of your initial histogram. These things happen to your raw data to create the histogram that will then be compared to the computer's lookup table histogram. Okay. So segmentation is going to, well, I mean, what's the term mean, right? When you segmentation, kind of one thing goes here and one thing goes there. It's kind of looking for, and in radiography, it's looking for noise. It's looking for densities that are way too bright, that might represent metal, or way too dark, that might be raw radiation, you know, or air that is outside of the part. PPR is very similar to that, but it's based mostly on the CR unit trying to identify separate areas of collimation. You don't have that problem in DR because you only collimate once and you only do one view at a time. Where you'll see in the next couple of slides, there's a picture of a finger, and it's very common, right? I mean, you do this. Do you do a separate finger on a separate cassette for every view? Like 3 10x12s for AP, or I should say PA, oblique and lateral finger? We used to have to do that. Now the systems have algorithms where you tell it, I'm going to have 3 sort of rectangles, each a field of collimation, but things still get messed up if the computer cannot see the borders correctly or even assess them. So here's an example of PPR, right? Obviously this is not DR because you can't do this in DR unless you're able to move so fast, right? Like the Flash. I don't even know if the Flash could do this, right? Get in there, change 4 views all in the same exposure time. But what happens here is it can cause what's known as a rescaling error. So scaling is the process of creating the optimal contrast. We've talked about scale, long scale, short scale. So when you choose a part, the lookup table histogram has a particular contrast in mind, a particular scale of contrast. But things can get messed up, and this process known as rescaling, which is assessing your contrast and changing it to the optimal contrast, might not work correctly. So that would be bad communication at that point. So rescaling, again, is changing the scale of contrast that your image would have with what the computer thinks is optimal. Right? Sometimes doesn't work if it can't figure out the borders of collimation. Exposure field recognition happens in both CR and DR, and it's looking for essentially the same things, but it goes beyond just borders of collimation. It's actually looking for densities, like a hip prosthesis that shows up really, really bright because it's metal, or raw radiation, again, that's outside of the collimated field, or even within the collimated field, but outside of the part. I mean, unfortunately, it can't be like, pre-K, where you take the kid's hand and you trace their fingers. We don't have collimation that good, right? We can only do a rectangle. But there will be parts between fingers and, kind of outside of them where you just have raw radiation striking the image. And that's essentially going to turn into bad data if you don't recognize that. So all these things come under the heading of volumes of interest. We're looking for places where you see maybe a lot of bone and recognizing that it's bone versus metal versus a lead apron, all those things that attenuate the beam a lot and would normally cause a bright density. Some of that information you don't want. Some of it you want to make sure that you do have it. So it kind of works a little bit both ways. All this stuff will be accounted for, and you'll see in a couple seconds, in your histogram. And of course, you can't go into your computer and actually pull out something that looks like a graph, right? So we're using this representation of your histogram as something that looks like a bar graph, when in reality, it's memory locations, right, in your computer, right? It just helps to see it graphically for us to kind of understand what's happening. So poor field recognition causing a rescaling error. The idea behind this slide that I added just this morning is the technique was good. That's the assumption. You use the proper KV, all those good things. It's just that the computer didn't understand the EFR. And maybe that's because they were diagonal. Maybe could be a lot of different reasons. Here it figured it out and everything's okay. This can easily happen when you do bilateral hands and you do them both at the same time. I know you're trying to save radiation, but maybe you can cause a problem in CR/DR when you do that. Here's another example. You put that little lead square up against the person's back when you're doing a lateral lumbar spine to kind of cut down on the scatter. But if you have this density maybe that's caused by that lead strip being in the field, maybe the computer gets confused. I'm not saying don't do it. I'm just saying be wary and look at your images. So your histogram is created by your exposure. And you end up with this raw data here. It has already gone through some pattern recognition. Certain things may have been removed that we'll talk about in a few minutes. some of the spikes may have been taken out, things that represent extreme brightness levels or extreme darkness levels. And you're left with a histogram that can then be compared to what's optimal. One of the things we're going to do in the lab is try to mess this up. We're going to try to like do a toe and process it under a skull. You know, we'll purposely do what's not recommended. Any questions so far? We're okay? So often your histogram can be depicted as a curve instead of like the bars that you saw. It's basically the same, right? If I go back a slide and I, drew on this and drew a line over the peaks and valleys, etc., I get something that kind of looks like this here. How do you read these histograms? Left side of the histogram, brighter, lighter pixels. Right side of the histogram, they get darker and darker. And each histogram is usually assessed with a starting and an end point, except we call it S min or S minimum, or S maximum or S max. And we can move those points around. Like you'll notice on the right side here, the S max is not at the actual end of the image, right? It's not here. Because in this particular example, you have a spike. You have a spike representing, this arrow should be a little bit longer, representing the black raw radiation that's actually outside of the image. And the system knows to take that information. The hardest thing is knowing that that is there, right? If it doesn't pick up on that, then you have a problem. But if the system, which is designed to try to pick up on an area of raw radiation, create this spike, then remove it from the actual processing. We'll talk a little bit more about this in a second. So we're going from lighter areas on the left, darker on the right. So for example, here we have a very bright area, which represents one of the, T-spines, vertebra, not T-spines, one of the T-spine vertebra. So it's linked towards the left side of the histogram. So here's an example, right, of a pretty common histogram. This is not the only histogram. They take, they fall into basically three types that we'll talk about. But type 1, which this happens to be an example of, is a histogram where you have a spike on the right side. So something that would be very, very dark. And this particular spike represents raw radiation. How might this occur? Like it says here, you might have a part that's small, doesn't have to necessarily be a small chest, that's just the example here, but it doesn't fit entirely over the image receptor. So the image receptor is then subject to raw radiation, basically radiation that hits things outside of the actual part. Why is this important? If this spike is not recognized, your overall image might be too light because the computer will say, oh, this is really dark based on this spike that I missed. I'm going to make everything lighter to compensate. So the idea is it captures this and says, oh no, that's information that I don't want to pass on to the rest of the reconstruction process. I'm going to set my S max at the point where I have the darkest, grayest pixel, but still represents anatomy and not just pure raw radiation. And I'll do that on the left side when I set my S minimum, which is not pictured on this image. And this kind of gives you a representation, right? air / lung tissue, chances are it's going to be darker. That's why it's on the right side. Yes.
So like if you collimate on the, let's say a hand, but if you collimate like here, everything would be brighter. Like let's say it doesn't like my hand is like this.
So yeah, what can happen is if your field is open too much, right? So you, let's say, way past the tips of the fingers. That's going to cause a spike, that's raw radiation, that the image received, it's still within the overall collimation, and it can cause the image to be too light because if that darkness is not picked up, it will try to lighten up the entire image and treat it as if it was anatomy, when it's actually raw radiation. Here's an example, no spikes. That's nice. This is what we try to turn type 1 into. So this is actually type 2. A type 2 histogram doesn't have any spikes. It means that the part was pretty much filling up the entire image receptor. By the way, this is a rationale for making sure that you use the correct cassette size and that you don't undercollimate, right, and leave too much space between the anatomy and the image receptor. So you have an S min and an S max. And that radiation that normally would have been removed by exposure field recognition is not there to begin with. So notice how this, once it gets chopped off, essentially becomes this image here. Right? This is a better starting point before you even get to that comparison between your histogram versus the lookup table histogram. It's kind of like we need to fix your histogram first before we even allow it to be compared to what is thought of as the optimal contrast brightness based on the lookup table. So here's a type 3. And they're all summed up in the next slide or two. I have type 1, 2, and 3 all together. But here we have 2 spikes. We have raw radiation on the right side. We've already seen this as type 1. Now we have excessively bright, basically white pixels that are useless to us and will not help in the processing. So that ends up getting eliminated also. So we're talking about things like barium, metal, right? Bone. And again, our S min comes at the point where we just start to turn gray. Think of the lightest gray that you can possibly have, but not white. And here, S max is the darkest possible gray that's not completely pure black. So things like, the lead shield might be in here also. That's why it's hard to shield in CR sometimes, because if one edge of the shield, and this happens all the time on a chest x-ray, you have it down here, you're protecting the gonads, but the bottom of the shield shows up in your image, it could cause a rescaling error. This goes against everything we were taught when I went to school. There used to be a term known as you had to show evidence of shielding. If they didn't see the shield, then how do we know you shielded? So now there's a little controversy here. Yes?
I was going to say my clinical instructor actually spoke about it. She's like, senior year, she wants evidence of shielding. To me there.
Yeah, and I think you should still do that for now. But and hopefully the systems are smart enough, especially on a chest x-ray, because that's a classic example of where this type of rescaling error can occur. hopefully they have built some logic into the algorithms to say there might be this wavy, curvy white lucency at the bottom of the image. Watch out for that. It's probably an apron, ignore it. So it's beyond my level to turn that into math, but that's what happens. And what are you left with, right? You're left with an S-min on one side and S-max on the other. Part of the process where you decided at what particular pixel brightness am I going to set my S-min or set my S-max, that's known as setting a threshold. Right? So you just determine where am I going to start counting pixels? Like what is that lightest gray level before I call it the minimum? Or what is my darkest grayscale? So that area becomes our basic data that we're going to butt up against the lookup table. And interestingly enough, the average, which would be in the middle, is known as your exposure indicator. So I suppose I could have talked about this a long time ago when we talked about exposure indicator, but I was able to hold back. But your exposure indicator is really only as good as the algorithms did a job at fixing your histogram and establishing good thresholds that turned into an actual S-min and an S-max that are realistic. If this included the spike in this example, then our exposure indicator is out of range, and it may not have been because of the exposure technique, which is what we usually think it is. Here's a summary of our three that we kind of talked about throughout our lecture so far. Type 1 has a spike based on raw radiation or air. It's information, as you can see here, this area is not sent to the lookup table. It's like, don't even include this. When the system gives you a spike, it actually worked. Right? It's when there was raw radiation that didn't get picked up by the system that you have a problem. Type 2, no spike. The S-min, they call it a tail sometimes. So the tail is towards the left side. And this third one here, we have a tail and a spike. Tail is barium, metal, lead apron, things that would show up absorbing the radiation so that you would get too bright of an area. Yes?
There when type 4 when we have tail but without ball exposure.
There might be. There's probably subcategories. When you review the image, you might not like the image. We talked about this, right? You might want to adjust the scale of contrast yourself. So how do we do that? Sometimes we use the mouse. Sometimes you can actually plug the information in. Other times you might actually see a histogram with an S-curve on it. The S-curve represents the scale of contrast. And you may be able to actually click on it and move it around. But what you would be doing essentially is changing the slope, changing how steep that S-curve is. And let me show you what that will do. Okay. So example A and B are examples of the technologist changing the slope of the S-curve. If you have a steep slope, which is example B, picture that this steep slope is kind of going through these grayscales. So I wish they drew this with sort of a gradient of different grays versus a couple of green boxes, because that's not the way it's supposed to be. Picture it going from, you know, dark to light or light to dark with lots of different grays in between. So this steep slope is going to travel through that much faster. If you create a steep slope, that's going to represent itself on the image as being a short scale, high contrast image. If you adjust the S-curve so that the slope, you don't really see this, maybe you don't, especially when you're moving it around, but imagine that even if you don't have this S-curve, it's happening in the background. If you shallow that out, now you're traveling kind of slower through, spending a longer period of time going through the grayscales. That represents on the image as a longer scale and a lower contrast. Now, of course, this is happening after you already have created an image. That pre-processing has already occurred. You're just asking the computer to reprocess the image using the same algorithms it did before to try to change the contrast a little bit for you.
Is that what we would call rescaling?
It'll force the rescaling process to happen again. But rescaling happened before you ever did anything. Rescaling occurs when your data from your histogram is compared to the lookup table histogram. And then the lookup table histogram says, no, I think your scale of contrast should be this. I am going to rescale it. A lot of times you'll see this, especially in DR, you get this gray washed out image. There's examples of this that I will continue on when I videotape myself with the rest of this lecture or give it somewhere else. Where you get that gray washed out image that kind of like blinks and suddenly looks better. That image is the rescaled image. Yes?
After you change the scaling, does that count as a post-process? Or is that still pre-process?
See, that's the first couple of slides. It's a lot of people think of it as post-processing, but it's really doing the same pre-processing again. Just maybe constraining it a little. Or asking it to lean towards a longer scale or lean towards a shorter scale. Essentially, you didn't like how it did the first time. Yeah.
So what about like when you send an image somewhere else? Is that post-processing or just?
When you send the image like into paths,
Yeah, like, or what is that process called?
I'm not sure if I understand the question, but I can tell you that your image has to be transmitted from your workstation and then kept somewhere, right? Because radiologists want to read in their little room. They don't want to come down to where you are. And there are rules that govern the grayscale. Part of the DICOM rules that we'll talk about in another class make sure that your grayscale that you see matches the grayscale that they see. And a lot of it has to do with, let's say you had two radiologists, one in New York and one in California, that are both, looking at poor Luke Perry's brain scan and trying to see what happened there. You want to make sure that both monitors have the same grayscale, so they're looking at the same image, for example. So there are some rules like that, but the rescaling process has already occurred. Now, if a radiologist or whomever wants to still tweak the image, they're perfectly able to do that. But they may not be able to get back to the raw data completely, which is why we have to be careful about, just trying to make the image look pretty on our monitor when it goes, to some much fancier workstation, after you click it into PACS. Okay, any other questions for now? Because this will continue. No? All right, guys. I'll see, maybe not some of you in the afternoon. I guess I'll see you guys next week. Okay.